So good morning, everybody. Thanks everybody who showed up today. And Chen and I would like to welcome you to the first seminar of the fall series of the Bureau Seminar Series. So thanks everybody for showing up. And we've got an exciting semester, I guess you could say, planned for you guys with a lot of cool talks on Friday. And we're going to start off our seminar series with one of our very own, Hongliu Zeng. So let me get to reading his bio. I mean, many of you know Hongliu because he's been a Bureau feature for a very long time. He's a senior research scientist for the Bureau of Economic Geology, who works primarily for the STAR Research Group, in addition to working on projects for other Bureau groups and industry contacts in China. His research interests include seismic sedimentology, seismic chronostratigraphy, attribute analysis, and machine learning. The longtime focus of his career has been to push applications of new interpretation concepts and techniques in seismic stratigraphy, high-frequency sequestration, and reservoir prediction. So Hongliu, I'm really excited for your presentation today, and you are welcome to go ahead and start sharing your screen. Oh, and if I could ask everybody else, please hold your questions until the end. You're welcome to put them in the chat, or just wait until the end of the presentation. Thank you.
So could everybody see my presentation, this title page?
Yes.
Okay. Yeah. Good morning, everyone. Yeah, and welcome to my seminar. And this morning, I will discuss the impact of sedimentary facies on machine learning of acoustic impedance using seismic data, challenges and solutions. So first thing, what is machine learning? Yeah, this is a branch of computer science that gives computer the ability to learn without being explicitly programmed. This is from Samuel 1959. And there are three types of machine learning: supervised, unsupervised, and reinforcement. And what we are interested in supervised learning, including classification, regression. And today we are going to discuss regression. So generally speaking, for general science, machine learning is train the data to predict. But for seismic lithology or immersion issues, we want to train seismic attribute to predict the rock properties, for example, acoustic impedance. So there are some potentials and pitfalls. Of course, there are some obvious advantages of machine learning. First, no formula necessary. And the second, it takes advantage of computing power. Yeah. And thirdly, it can be better than model-based inversion. And we observe the training score as high as 0.93. Yeah. And secondly, there are some pitfalls. Yeah. Majorly, that's the model accuracy depends on quality and the quantity of data. Yeah, there's always a garbage in, garbage out issues in a geologically or facies complex formation. Yeah. So I'm going to talk about start with some motives. Yeah, why we choose to do this project. And then I will introduce you a geologically realistic model as labeled data. And introduce you random forest regression as our algorithm, and show you some results and the field data tests and some conclusions. So the motives, yeah, we know the machine learning is popular those days in many aspects of geosciences. Now we can construct the seismic inversion of lithology as a regression problem. The goal is to predict pseudo well logs acoustic impedance from post-stack 3D data. But there are the problems. Yeah, because machine learning based inversion right now has been limited to the individual trace locations or in situ cases. So I ran through literature search, and almost every article start with the choose of algorithm, like a neural network or random forest or something else. Then find some wells with the impedance log and the seismic trace, then train those data to predict the impedance log at the well size and expand that to the whole volume. Last year, we ran a test, and unfortunately, we found that this trace by trace training approach can be very unstable. Yeah, that means the prediction can be brilliant or disastrous, depends on well location or facies. In this example, we have 3 wells for machine learning. Each time we choose 1 well and get the 3 results. And you can see here, compared to the true model, that the quality can be marginal, can be good or poor. Yeah. So that means that in the machine learning scheme, the geological factors or facies factors must be considered. We are fortunate to have a very old model built a long time ago in South Texas. And this field have depositional settings, micro-tidal shoal zone system. It's very similar to modern Matagorda Bay. And we run well log analysis to correlate high frequency sandy units. And run facies analysis, and we recognize a total 18 subfacies. And we have a rock physics model from log analysis and convert facies model to the impedance model. So eventually, we have a pair of 3D models. On the left is impedance model. That's our true model, supposedly true model. And on the right is a synthetic 3D model. Yeah. So this pair of data are our perfect candidate to use as a labeled data to test machine learning software. So because when we built this model, it involved a lot of facies. So what's the facies? Yeah, I like this very simple idea. The facies is a sum of total characteristics of rock, including chemical, physical, biological features. And that means we have a lot of parameters can be used to describe facies, including lithology, petrology, sedimentary structure, bed form geometry, thickness, sand percentage, and others. And in this study, we found the sand percentage is particularly useful to describe facies. So here, this on the up, the sandstone facies map, sandstone percentage map constructed with the well analysis, and it shows the sandstone percentage can change from 30 to 60%, depends on facies. Yeah, there's the flat plan facies and the shoal zone facies and the transition facies. And compared to the speckled sand bodies, you see that have a lot of similarities there. And this is a flat plan, and this is a shoal zone, shore phase, and in the middle is a transition zone. So algorithms, yeah, we choose a random forest regression, and it's written by Python in an open platform network with the support of machine learning labs. So there have been a lot of discussions. What's the best algorithms? Yeah. After some testing and discussion, we believe that algorithms is not most important issue, because if if an algorithm fit your problem, it can be many. You have different choices, but the more important thing is the data. Yeah, the quality of data, quantity of data, and understanding of the data. Yeah, those are by far the more important things. So we spend a lot of time on the data analysis. So our algorithms, random forest, it's based on the decision tree. Yeah, decision tree make a prediction based on prediction by sorting data by prediction error, just pretty much like a point sorter. And the random forest is a group of trees. By using a bootstrap or random sampling, and make a lot of predictions and then take average as a final prediction. Another important issue is what kind of features are effective. We run a literature search and basically believe 3 types of attributes most useful. Yeah, they are the seismic trace itself, and the windowed attribute that will take care of wavelength effect, and the frequency panels that will take care of tuning effect. Actually, there are many other attributes can choose from, but at this moment, we are still in the testing, so we're not going to discuss today. Eventually, we select the 40 attributes. The seismic trace itself, 3 frequency panels, and some time-shifted volumes, and especially we have 4 attributes that potentially relate to geology. XYZ probably relate to facies, and the stratoslice index or relative geologic time that may relate to stratigraphy. Then we split the labeled data into training, validation, a testing subset. Yeah, there are some flexibilities here. For training, we can take anything from 1 traces to 1,000 or 2,000 traces or pseudo wells. Yeah, and the rest is a validation and testing set. There are some flexibilities again here. So the key parameters to evaluate the quality of training and the prediction, including the R2, that's so-called explained variance, or we call it the recovered signal. Yeah, its meaning is very straightforward for geologists. And we can use 1 minus R2 as a standard prediction error, or sometimes use root mean square error. So firstly, we need to sample the training data set. It can be from one well from up to 1,000, 2,000 wells, depends on different exploration to development stage. For example, this 1,000 well case, I have a well spacing 29 acres. That's typically development stage. So we run the testing and validation to train the hyperparameters for the system. And here the horizontal axis is number of wells, vertical axis is the R2 score. And on the left is the training, on the right is validation. So 2 observations. First, the R2 will increase with number of wells, and for training and the validation, and there is no sign of overfitting. And then secondly, the R2 will increase with number of trees. So number of trees from 1 to 200, you can see the R2 increase continuously. Yeah. So eventually, we figure that the tree depth 10 and the number of trees 100 probably fit the most of purpose. Then we run some testing to determine the characteristics of this machine learning system, how the response to geology and training data. Here again, horizontally is number of wells, vertically is R2 score. So 2 observations. First, R2 will increase with the number of wells. from 1 well to 2,000 well, the average R2 will increase from 0.5 also up to 0.9. So from good, stable to excellent. And secondly, R2 will stabilize with the number of wells. That means that in 1 well, the testing results are very scattered. The R2 will be from 0.2 to 0.6, right? Up to the well number 15, we start to see stable result. Yeah, stable result. So 2 lessons. First, we need a large number of training wells for good results. And secondly, the training with the sparse well will lead to low score and unstable results. So we also evaluate the results with some benchmark. So up here is the impedance section from true model. And this is the amplitude data synthetic. And that has only marginal correlation. And the linear regression, correlation improved a little bit, but still kind of low. And the model-based inversion is our industry standard. And but it goes to 0.6 or something, R2, and it's not super. And you can notice the lack of high resolution details here. So how about the machine learning? So machine learning results is that if we use 1 well, R2 is like 0.5 in this case, but we know it's highly unstable. And the 5 wells, R2 is 0.68. And this is already outperform the model-based inversion. And if we have 500 wells, R2 will be 0.9 also. Yeah, it looks very similar to the original model. Yeah, almost perfect. And please notice the high resolution information we get from it. But again, yeah, this 1 well or a few wells will generate unstable results. For example, here 3 wells get the 3 different prediction, and they're running different quality. Yeah, and we can map the R2 and the prediction error to show the quality for prediction, and actually that's controlled by facies pattern. Yeah, on the left, the R2, in the middle is prediction error, on the right is facies or sand percentage map. So you can see the similarities there. So the R2 can be very high to very low if you measure the trace by trace. This is different from our original expectation. The reason is if you sample the well from different facies zone, and it will determine the final results. Yeah. So it shows the facies control. If you different time choose different well, you would get the different results. This facies induced instability can only be removed if more wells are used in training. Here, there's 1 well, 2 well, 5, 10, 50 to 500. So until we use 500 wells, we remove most of the error and get the high correlation. So a side note, yeah, we promote to use geological features as a training attribute, and the campsite is important or significant. Yeah, we use 4 geological features here, but in the 1 well case, XY is useless, but the Z and the stratoslide index is meaningful. When we increase to use 50 to 500 wells, that becomes more and more significant. Yeah, and in fact, if we remove those features, our training result will suffer. Yeah, at the maximum, we will lose like 5% of variation. So that's significant. So we have a big challenge here. The training uses small labeled data set tends to be low score and unstable, which limits the value of methodology. Yeah, and this is similar to the old story of a blind man and an elephant. Yeah, use a single wells, a few wells, like a sample, a very small sample, like those men. But unless you collect all information, you're not going to get the whole image of this elephant. So fortunately, we have a different approach. Yeah, we can prepare a large training set to try to ease this problem. And this approach is advocated by people in recent years, like this one, Das et al. 2 years ago, uses statistical modeling to get the data, get the training data. So this is our workflow. First, we select data. Yeah, 1 to 10 wells from representative facies zones or study area. And secondly, create sequential Gaussian simulation model. And 3, extract wavelet from field seismic data. And 4, create a synthetic seismic model. 5, try to test your random forest model. And finally, apply this model to field data to predict impedance. Here is a model data test. You choose some wells from your true impedance model and the seismic traces, but instead use those data to directly predict the impedance volume. You go another way. You use wells to create the statistical model first. This model may look different from your original true model, but they share the similar spatial correlation. Then use extract wavelet, you create the large synthetic data volume. Then you can test the quality of this synthetic data by trend for impedance. That comes out pretty good. Then you use the model to convert field seismic data to get the predicted impedance. And you can see the predicted impedance. The outcome is very similar to true impedance model. Yeah. And this is another way to compare the result. Yeah, this vertical sections and horizontal slices. And you see on the left is a true impedance, on the right is a predicted impedance. That looks very similar. So we have several well field data tests to show the value of this approach. The first examples from tertiary Bohai Bay basin in China. On the up is the field data. On the left is training wells. On other wells are blind testing well, and you can see the original seismic data not good fit to gamma ray here, basically functional impedance. But after the synthetic model training and predict from field data, that's the output we get. In the training well, of course, we got a very good result, and gamma ray logs fit very well with the seismic. But for plant testing data, we got a very decent result. Look at those sand bodies are characterized by the red color, and shells are characterized by black color, and they are relatively high resolution. And the second example is from the CO2 pilot project in Tesla merge 3D lower Miocene. Here we choose 5 wells with good quality sonic log, and together with the horizons picked from seismic volume, we built this statistical model as our training model. And then we test this impedance model. On the right is an impedance model. In the middle, synthetic data. On the left is a predicted impedance. With the correlation with the R2 equals 0.82, you see the results are pretty good. Yeah. And then we have a blind test well. Yeah, this well is almost 4 kilometers away from on nearest training well. And on the right, and the original seismic field seismic data, and you can see the gamma ray doesn't correlate to amplitude very well. On the right, there's a predicted impedance by machine learning, and you start to see the sandstone shell line up by different color. Yeah, bright colors sand, cool colors shell. And if you run the cross plotting here, you can see the V shell and the predicted impedance. I have a kind of decent correlation here, very correlation coefficient 74%. And this kind of results are very useful to really do the sand mapping, sand volume mapping or thickness mapping. That's very useful for facies analysis and the CO2 sequestration. And in this example, we mapped the top sequence, and you can see we figured the sandstone thickness here is from 35 to 80 meters, and it shows two big deltaic sand bodies. They are excellent CO2 reservoir target. And the third example is on Wilcox in South Central Texas, where we're interested in these volumes because in deep water basin in Gulf of Mexico, there are huge amount of deep water sand, and this area is on the slope, and we want to know what happened here in the lower Wilcox. So we choose 6 wells again with good sonic logs, and build this simulation model. And on the right, the synthetic model. On the left is machine learning results. Not bad. So then we test by using field data. On the right is field data. On the left is a predicted impedance. Again, you can see quite different. Yeah, quite different. And here we need to use the blind test to really show the value of this methodology. So this blind test well shows kind of a correlation between predicted impedance and the log impedance. Yeah, you see the trend there. But we want to see more detail. Then we plot the gamma ray. The gamma ray, that's a lithology versus velocity. Yeah, then we see the kind of correlation. We see all those red, the red amplitude. They are predicted the high impedance sand, a lot of them. And also we can see the low impedance shell characterized by black amplitude. But we do have some trouble to separate the low impedance sand. That's in the transitional zone. But because in this area, most of sand bodies are low stand, high impedance sand. So this result is still pretty useful. And then we can see some horizontal result. This is from up Wilcox. On the left is amplitude image. That doesn't tell us much, only except this inside the valley. On the right is machine learning result. You can see clearly the fluvial system and the delta systems on the shelf, and the inside the valleys, and the slope systems, slope fans. And the other images, this is still up Wilcox. And similarly, you see big sand bodies, fluvial, delta, the slope, and the fan. On the right is from middle Wilcox, and this one looks a little bit different, less sandy, and probably that's because it's well dominated by core analysis. But the slope fan, the basin fan, and they looks very similar. But we are still in the process to take a look for cores and have a more detailed facies analysis. So the conclusions. First, geological realistic model is useful to guide machine learning based inversion. And the number 2, facies of maps of R2 and the prediction error demonstrate facies control. Number 3, geologic features add value to machine learning based inversion. Number 4, a good inversion is backed by a large labeled training data set. And then number 5, small training data lead to poor and unstable results. And finally, a large synthetic training data set may improve the prediction. For those of you who are interested in this research, we have recent publications in the interpretation journal. Finally, some acknowledgement here. We cannot get this kind of result without support from projects and the colleagues, STAR in GCCC, and some people gave us very positive and constructive comments, and the companies donated software for our free use. And the staff sincerely appreciate. Yeah, and I want to stop here and take any questions you may have.
Thanks for a great presentation, Hongliu.
Thank you.
Yeah, if anybody has any questions, please put them in the chat box or unmute yourself, and I'm sure Hongliu will be able to answer them.
Hi, Hongliu, this is Mohsen. Thank you for your nice presentation. In one of your slides, actually several of them, you were talking about R2 values based on 3 wells 1, 2, and 3, and then you were saying that depending on which well you used, you basically had different R2 values. So, so that I understand better, you use each well and then you train your data using a synthetic forward model based on that one individual well, or did you just use one training well? I don't quite understand. So when you train your machine learning from one well, are you actually using the traces from that one well to create multiple forward models? How do you actually train your data with just?
Okay, so here we actually discussed two methodologies to build the training data set. First is by use those wells only. That means you use impedance log and the well side seismic trace only to train your model and make a prediction for the whole volume. And another approach is to use this one well or several wells as a seed well and build the statistical model. That means you have to use, for example, the sequential Gaussian simulation type things to really make a prediction simulation between the wells to create many traces that probably reflect a more reasonable spatial correlation between wells that doesn't catch up by well data only. So that's the key for improving the results by using large synthetic synthetic training data. Yeah.
Thank you.
And of course, you can use 1 well, 2 well, 5 well, and more well. The bottom line is if you have more wells, please use it. Yeah, because based on 1 well, it's not very stable because it has very only limited the facies information. That may not very representative. Yeah.
What sort of quality control do you guys do? I mean, like, I'm sure you're getting like logs from multiple different vendors and different equipment, and so how do you quality control the traces that you receive, or do you?
I'm not quite sure what's your question, but
so I mean
basically we build that model, so first make sure that the model is good quality. So your impedance, you build the impedance model should come back pretty good with the synthetic data, right? And more importantly, then you have to use the blind well test. You cannot use the training wells to say, okay, your training result is good or not. you have to use the blind testing well. That means those wells didn't be used in the training, but they are there, and you just use them to see how accurate your prediction will be. And that probably is a more practical and useful method.
Thank you.
Hongliu, I have a question.
Yes.
Were you able to, in your research, were you able to kind of figure out an optimal well density for generating a really good stable model? I mean, I know that you said, 2 wells is bad, 5 wells is bad, 500 wells is amazing, but there's like, there's like 498 wells in between there. So is there a particular density that is best for using?
Yeah, there's a general rule. If you use more wells, you will get a better result. But we should understand that in real applications, it's not very often we can get that many wells. Even if you have that many well, that's no guarantee you can tie all those wells with good tidal seismic data. That means you will add some noise, not signal there. So that's probably not good thing to do. But probably the better approach is that you have kind of adequate control for your seed well, like a 5 well, 10 well, then use a synthetic model to build a real big training model. Yeah, in that case, you will get kind of reasonable and highly stable result. That compared to inversion is still quite good, but of course it's not super high like a R2 over 90% or something. That's really not really hard to get unless you have like 2,000 wells, each one have a good tidal to seismic, right?
Gotcha. Cool, thanks.
Hongliu, this is Ramon. Thank you for your good presentation. I really enjoyed it.
Thank you.
I have a question about the testing wells. I was wondering, is there an optimum geographic distance, for example, that a testing well should be away from the training wells? For example, can you be too close to the training wells to where you're not doing a good test, or is there an optimum distance where you expect the geology to change enough?
Yeah, if we want to go to correlation, theoretically, yeah, the closer your testing well, the better, right? But that's not real control of your quality. You always want the testing well as far as possible, and they still get the good result, right? So I guess for example, in CO2 sequestration data situation, probably if we can get the good result, like in 5 kilometers, 10 kilometers, that would be very, very good. Yeah.
Okay, thank you.
Yeah, I guess, yeah, for those of you who have a question, yeah, you can send me an email and I will try to answer. And yeah, one of the purpose to have this kind of presentation, always want more discussion. I know that this study is not perfect. Yeah, a lot of issues. It's ongoing.
Hongliu, I have one other question. Have you
Yes.
looked at resistivity logs as one of your attributes for your vectors that you're using? Or is this also only based on acoustic impedance?
Resistivity? I didn't use resistivity.
Well, okay, that was my question. Could you consider, for example,
yeah, sure, but
yeah.
But
Sorry,
the issue here is, yeah, we are trained impedance log, full impedance log. So of course we can train resistivity log for resistivity log, but probably only if you have a good correlation between resistivity log and acoustic impedance log. you will get there. Because seismic basically is the impedance. Yeah. If you don't have any correlation there, I don't think you can have a good prediction. But in my observations, in many cases, actually your resistivity correlated pretty good with the velocity, especially after the velocity after the compaction. Yeah, that were often very highly correlated. In that case, I think, yes, definitely you can try. Yeah, and expect some good results out of it.
Hey, Hongliu, this is Mark, and nice presentation. But to follow up on that question with using resistivity data, just in general, what about hydrocarbon impacts or changes in fluid on this model?
Yeah,
and
actually, hydrocarbons is noise to us because that will reduce the velocity and impedance and makes kind of false impression. Yeah, false trap, if you say. So I would say, yeah, that's kind of noise. We have to pay attention to it. Yeah, but because because I think most of the time we can recognize that and try to avoid.
Okay.
Hongliu, it's Tong Wei. And
Yes.
this is really good, very good presentation. And I just wondering, you showed the 3 cases studies, and for the CO2 sequestration, for the sandstone body prediction, and use the machine learning. Can you emphasize or describe more what the new things we learned from using machine learning compared to conventional method which you used before?
Okay, yeah, probably put it simple. I have two major messages here. First, machine learning can be better because with several wells, I can easily outperform the model-based inversion. That's the industry standard. Yeah, you don't have to have a perfect tie between well and seismic data. If you use a synthetic training, so it's actually easier to do than model-based inversion. But we have to do this very carefully because, as I said in the beginning, yeah, if you do something wrong, you get the garbage in and garbage out. Yeah, still that's a risk to us. Yeah, so don't fall into that kind of a trap, and always use the blind testing to show, yeah, you really got a nice result. Because some publications publish the paper, when we read them, they will say, okay, I use one well to train and use another well to test. Oh, you see very, very good, but it may not be the case. Yeah, this is what I mean.
Okay, I think if there's no more questions, y'all know how to find Hongliu if you happen to think of one after we close out today. But I guess we'll finish up for today's seminar. Hongliu, thanks for a great presentation, for kicking us off right for the fall. And y'all can rejoin us again next Friday for a presentation from Tony Larson.
Thank you very much.